Now in this lecture we'll find out the radius of the small circle. The drawing the right triangle ABC. In addition, you know that side AB equals to 6 units in its length, side BC equals to 8 units in its length. Inside the right triangle ABC we have this small circle and we have this big semicircle. Our mission is to find out the radius of this small circle. So first of all, we will implement the Pythagoras theorem on this right triangle ABC. According to the Pythagoras theorem, in the right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. The hypotenuse in this right triangle ABC is AC, therefore the square of the hypotenuse is AC square, and AC square must be equal to AB square plus BC square. So I write it down. Here by PT is abbreviation for Pythagoras theorem. So in the right triangle ABC, AC square equals to AB square plus BC square. Repeat again according to the Pythagoras theorem in the right triangle ABC. AC square equals to AB square plus BC square. AC is the missing side, so we leave it as it is. AC square equals to AB square. AB is 6, therefore AB square is 6 square, that is 36, plus BC square. BC is 8, therefore BC square is 8 square, that is 64. So in total we found out that AC square equals to 36 plus 64, that is 100. So AC square equals to 100. We take out of this equation and find again that the missing hypotenuse AC is equals to the square root of 100, that is 10. So actually found out that the length of the hypotenuse AC is 10 units. So AC equals to 10. In the next step, we define the relevant points to this question with letters. We define the center of this small circle, this point as point P. Likewise, we define the center of this big semicircle, this point as point Q. We define the point of tendency of tangent AB with this small circle, this point as point N. Likewise, we define the point of tendency of tangent AC with this small circle, this point as point K. We define the point of tendency of tangent AC with this big semicircle, this point as point H. And finally, we define the touching point of this small circle with this big semicircle, this point as point L. Here we can implement all two. Repeat quickly on all two. According to all two, the lengths of two tangents for a common point to a circle are equal. In the drawing we have a circle, and this is the common point, point P. From this common point P, we have two tangents to this circle, tangent PA and tangent PB. According to this rule, all two, they are equal to each other. That is to say, PA equals to PB. We can actually implement all two in our drawing, because in our drawing, we have this common point A. From this common point A, we have two tangents to this big semicircle. We have tangent AB and tangent AH. And according to all two, they are equal to each other. So I know that according to all two, the length of tangent AB is equal to the length of tangent AH. According to all two, but it is given us the question that AB equals to 6. So we can write here that AB equals to 6. And for this equation, 6 equals to AB equals to AH. We realize that the length of AH is also 6. AH equals to 6. We can here that the length of this 97 AH is equal to 6 units. What is the length of the, this is 97HC. From the domain it is very easy to see that HC in total equals to AC minus AH. So HC equals to AC minus AH. AC is 10, AH is 6, so in total HC equals to 10 minus 6, that is 4. So HC equals to 4 units in its length. In the next step, we join points Q and H together by straight line. Point Q is the center of this big semicircle. Point H is the point of the big semicircle itself. Therefore, QH is the radius of this big semicircle. We define the radius of this big semicircle as B. Therefore, QH equals to B. Here we can implement rule 1. I'll take quickly on rule 1. According to rule 1, the tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing here we have a circle, and we have this is tangent AB that is tangent to this circle, that is point M, and we have the radius OM that is equal to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. Whenever a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule 1. We can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius QH that is equals to B. The radius QH is drawn to point H, that is the point of tendency of tangent AC with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius HQ. If AC is perpendicular to HQ, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Okay, so by doing this construction, we are going to do the right triangle, triangle QHC. In the right triangle QHC, we have this angle, angle C. Angle C belongs to the right triangle QHC. But angle C belongs also to the right big triangle, triangle ABC. So angle C is the common angle that belongs to both triangles, triangle ABC and triangle QHC. So we define the size of this angle, angle C, as alpha. So in the right small triangle HQC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we will focus on the right big triangle, triangle ABC. In the right big triangle, triangle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha. According to the sum rule, the sum of the angles in any triangle is equal to 180 degrees. In the next step, we will prove that the right big triangle, triangle ABC, is similar to this right small triangle, triangle HQC. So, okay, I write it down. We'll prove that the right big triangle, triangle ABC, is similar to the right small triangle, triangle HCQ. So those two right triangles are similar to each other. First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually, this is angle ABC. In the right big triangle ABC, and it is equal to this angle, that is actually angle QHC. In the small right triangle, HCQ. Split again, we should have found out that angle ABC, the big right triangle ABC, equals to angle QHC, the small right triangle HCQ. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to this angle, angle alpha, since it belongs to the big right triangle ABC, it will be defined as angle ACB. And it equals to itself, so if we relate to this angle alpha, since it belongs to the small right triangle HCQ, it will be defined as angle HCQ. Again, this equation means that angle alpha equals to itself. We just call to angle alpha two different terms. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle BAC in the big right triangle ABC, and it is equal to this angle, that is actually angle HQC in the small right triangle HCQ. So I'll put again, we found out that angle BAC in the big right triangle ABC equals to angle HQC in the small right triangle HCQ. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually proved that all the triangles in this big right triangle ABC are correspondingly equal to all the triangles in this small right triangle HCQ. Therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. And we found out that the right big triangle ABC is similar. This is the sign of similar to the right small triangle HCQ, according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in the small right triangle HCQ. And again, we derive that side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in the small right triangle HCQ. AB is 6, over HQ. HQ is V, it is the radius of the big semicircle, that is equals to V according to our definition. And it is equals to BC. BC is 8 over HC. We already found out that HC equals to 4. So in conclusion, we can find out that 6 over B equals to 8 over 4. 8 over 4 is 2. So we can find out that 6 over B equals to 2. Here we will multiply this equation by B. And we get that 6 equals to 2B. Here we divide this equation by 2. And finally we get that the missing radius B of the big semicircle equals to 6 over 2, that is 3. So we can find out that the radius of this big semicircle B equals to 3. Point Q is the center of this big semicircle, point B is the point on the big semicircle itself, therefore QB is also the radius of this big semicircle, that equals to 3. So I write it down. QB equals to 3. In the next step, we will join points P and N together by a straight line. Point P is the center of this small circle, point N is the point on the small circle itself, therefore Pn is the radius of this small circle. We define the radius of this small circle as A, therefore Pn equals to A. A is the radius that we are looking for in this question. Can implement here rule 1 because we have the radius Pn that is equal to A, the radius Pn is down to point N, that is the point of tendency of tangent AB with this small circle. And whenever we have a radius that is down to the point of tendency, then tangent P and tangent AB will be perpendicular to the radius NP. If AB is perpendicular to NP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. We join points P and K together by a straight line. PK is of course the radius of this small circle, that is equals to A according to our definition. Again, we can implement here rule 1 because we have the radius PK that is on to the point K, that is the point of tendency of tangent AC with this small circle. Whenever we have a radius that is on to the point of tendency, then tangent AC will be perpendicular to the radius KP. If AC is perpendicular to KP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 15. According to rule 15, if from an external point of a circle you draw two tangents to the circle, this is the common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. By drawing the two tangents PA and PB, we get here this angle APB. Again, this angle APB is created by drawing tangent PA and tangent PB to this circle. Then the angle that will be created between the two tangents, this is actually angle APB. This angle APB, its angle bisector, so the angle bisector of angle APB must pass through the center of the circle. So the angle bisector of this angle APB must pass through point O, that is the center of this circle. So whenever you draw two tangents to a circle, from a common external point to a circle, you will create an angle. And the angle bisector of the angle that is created by the two tangents must pass through point O, that is the center of this circle. So we can actually implement all 10 in our drawing. Why? Because in our drawing we focus on this common external point A. From this common external point A, we have two tangents to this small circle, tangent AN and tangent AK. And by drawing those two tangents AN and AK, we get a deal. This angle A. I repeat again, this angle A was created by drawing tangent AN and tangent AK to this small circle. And according to rule 15, the angle bisector of this angle A must pass through point P, that is the center of this small circle. Again, the angle bisector of this angle A that was created by drawing tangent AN and tangent AK to this circle, the angle bisector of this angle A must pass through point P, that is the center of this small circle. So, the angle bisector PA, of course, passes to point P, that is the center of this small circle. This is the implementation of rule 15 in our drawing. So we can write down that the angle bisector of angle A passes through point P, that is the center of this small circle. The angle bisector of angle A passes through point P, that is the center of the small circle. So if we define the size of this angle A is 2 theta, then the angle bisector PA bisects angle A into 2 halves. Each half must be equal to theta, of course. Okay, we'll continue to focus on this common external point A. On this common external point A, we have two tangents to this big semicircle. We have tangent AB and tangent AH. By drawing the two tangents AB and AH to the big semicircle, we created the same angle A. Again, angle A was created by drawing tangent AB and tangent AH to this big semicircle. Now we can implement rule 15. According to rule 15, the angle bisector of this angle must pass through point Q, that is the center of this big semicircle. Again, according to rule 15, the angle bisector of angle A that is created by drawing tangent AB and tangent AH to this big semicircle must pass through point Q, that is the center of this big semicircle. So I draw the angle bisector QA, and angle bisector QA, of course, passes through point Q, that is the center of this big semicircle. In conclusion, can I know that the angle bisector of the same angle A passes through point Q, that is the center of this big semicircle. So I write it down. I actually found out that the angle bisector of the same angle A passes also for point Q. it is very clear that the angle bisector of this angle A must pass also through point A. Again, the angle bisector of angle A must pass also through point A. You can write down that the angle bisector of the same angle A passes also for point A. In conclusion, we found out that the angle bisector of this angle A, passes for points A, P, and Q. So write it down. So if we found out that according to rule 15, the angle bisector of angle A passes through points A, P, and Q. But again, we should hold on that the angle bisector of this angle A passes for points A, P, and Q. But the angle bisector of angle A, this is of course a straight line. The angle bisector of any angle is a straight line, therefore, especially the angle bisector of this angle A, it is a straight line. So let it know. The angle bisector of angle A is a straight line. And we found out that all the 3 points A, P, and Q passes through points with the angle bisector of angle A. So therefore all the 3 points A, P, and Q are located on the same straight line, that is the angle bisector of angle A. So if I found out in conclusion that all the 3 points that are A, P, and Q are all located on the same straight line. And the straight line is the angle bisector of angle A. Again, the straight line is the angle bisector of angle A. Okay. In other words, you can also write down that line segment APQ is one straight line. Again, line segment APQ is one straight line because the 3 points APQ are located on the same straight line. Therefore, line segment APQ is one straight line. And because of the fact that line segment APQ is one straight line, it means that this is angle theta, and this angle theta is a common angle that belongs both to the small right triangle APN, and this angle theta belongs also to the big right triangle, triangle ABQ. So write it down. I found out that angle theta is a common angle that belongs to the right triangle A and P, and angle theta also belongs to the right big triangle, triangle ABQ. Okay, angle theta belongs to the small right triangle A and P, and angle theta also belongs to the big right triangle, triangle ABQ. So in the big right triangle ABQ, this angle equals to theta, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees. If 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on the small right triangle, triangle A and P. The small right triangle A and P, this angle equals to theta. This angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus theta. According to the sum rule, that the sum of the angles in any triangle is equal to 180 degrees. So in the next step, we prove that the right big triangle ABQ is similar to this small right triangle, triangle A and P. So I write it down. We will prove that the right big triangle, triangle ABQ is similar to this small right triangle, triangle A and P. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle ABQ, in the right big triangle ABQ, and it is equal to this angle, that is actually angle A and P, in the small right triangle APN. Repeat again, we actually found out that angle ABQ in the big right triangle AQB equals to angle A and P in the small right triangle APN. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both triangles, so we can write down that angle theta equals to itself as a common angle that belongs to both triangles. So if we relate to this angle, angle theta, as it is belongs to the big right triangle ABQ, it will be defined as angle BAQ. And angle theta equals to itself. So if we relate to this angle theta, as it is belongs to the small right triangle A and P, it will be defined as angle NAP. Okay, again, this equation means that angle theta equals to itself. Angle theta equals to itself. We just call to angle theta two different names. Angle theta equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually, this is the angle AQB. In the right big triangle ABQ, and it is equal to this angle, that is actually angle APN, in the small right triangle ANP. So I'll repeat again. Actually, found out that angle AQB, the big right triangle ABQ, equals to angle APN in the small right triangle ANP. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually found out that all the triangles of the big right triangle ABQ are correspondingly equal to all the triangles of this right triangle ANP. Therefore, the two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big right triangle triangle ABQ is similar. This is the sign of similar to the small right triangle ANP according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB in the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle ANP. And again, after we found out that side AB in the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle ANP. AB 6 over AN. AN is the missing side, so we leave it as it is. And it is equal to BQ. BQ is 3, it is actually the radius of the big semicircle, that is equal to 3 units in its length. Over NP. NP is the radius A of this small of this small circle. That is the radius that we are looking for in this question. In conclusion, we shall found out that 6 over AN equals to 3 over A. Here we cross multiply this equation and we get that 6 times A equals to 3 times AN. So here we will divide this equation by 3. Finally we get that the missing side AN is equals to 6A over 3 is 2A. So actually found out that this missing side AN equals to 2A units in its length. So I write it down, AN equals to 2A units. It is given as the equation that AB equals to 6 units in its length. AB equals to 6, AN equals to 2A, therefore the missing 9, 7, and B must be equal to AB that is 6 times AN that is 2A. So in total, NB equals to 6 times 2A. So I write it down. I shall found out that 9, 7, NB equals to 6 minus 2A units in its length. In the next step, we'll do a construction. That is to say, from point P, we will do perpendicular on BQ. Again, from point P, we will do perpendicular on BQ. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and BQ. This point is point Z. By doing this construction, we can detect quadrilateral NPBZ. Inside quadrilateral NPBZ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the small quadrilateral NPBZ, we have 4 right angles, and then according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we refer to quadrilateral NPBZ as a rectangle because it has 4 right angles. So I did know if we found out that this quadrilateral NPBZ is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NPBZ, side NP must be equal to the opposite side BZ. But NP equals to A, therefore BZ must be also equal to A. Likewise, according to the same rule, in the same rectangle NPBZ, side NB must be equal to the opposite side PZ. But NB is 6 times to 8, therefore PZ must be also equal to 6 times to 8. What is the length of the missing line segment ZQ? For the moment, it is very easy to say that ZQ equals to BQ minus BZ. So ZQ equals to BQ, that is 3, minus BZ, that is 8. So in total, BQ equals to 3 minus 8. In the drawing, we have an external notch between this small circle and this big semicircle. That is to say, they are touching each other externally at point L. And whenever, this point L, and whenever you have an external notch between two circles, you can implement rule 10. I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together must pass through their touching points. So in the drawing we have two circles and they have an external notch between them at this point P. That is to say they are touching each other externally at point P. The center of this small circle is at point M. The center of this big circle is at point O. And the straight line that connects the centers together is of course the straight line MO. And according to this rule 10, the straight line MO must pass for point P, that is the touching point. I repeat again, the straight line MO must pass for point P, that is the touching point, or MPO is one straight line. Again, MPO is one straight line according to this rule 10. We can actually implement rule 10 in our drawing. Why? Because in our drawing we have an external notch between this small circle and this big semicircle, that is to say they are touching each other externally at point M. Therefore, according to rule 10, we know that the center of this small circle is here at point P. The center of this big semicircle is here at point Q. And the third line that connects the centers together is of course the third line PQ. And this third line PQ must pass from point L, that is their touching point. Again, the third line PQ according to rule 10 must pass from point L, that is their touching point, or PLQ is one straight line. Again, PLQ is one straight line according to rule 10. If PLQ is one straight line, then PQ is also a straight line. But what is the length of PQ? PQ will be equal to PL plus LQ. Again, PQ equals to PL plus LQ. PQ equals to PL plus LQ. Why? Because PLQ is one straight line, according to rule 10. So PQ equals to PL. PL is A. The radius of this small circle, that is the radius that we are looking for. It is equal to A according to our definition. And NQ is 3. it is the radius of this big semicircle, this is equals to 3. So in total, I actually found out that the length of PQ is A plus 3. PQ equals to A plus 3. In the next step, I copy the right green triangle PZQ in a new page, and we'll implement the Pythagoras theorem with this right green triangle PZQ. Here by PT is the version for Pythagoras theorem. Side PZ equals to 6 minus 2A. Side ZQ of the green triangle equals to 3 minus A. And finally the hypotenuse PQ equals to A plus 3. So actually this is the green right triangle PZQ that I covered from the original drawing. According to the Pythagoras theorem, in this right triangle PZQ, PQ square equals to PZ square plus ZQ square. Again, PQ square equals to PZ square plus ZQ square. So I write it down. So PQ square, that is the square of the hypotenuse, must be equal to PZ square plus ZQ square. PQ is 8 plus 3, therefore PQ square is 8 plus 3 square, and it is equals to PZ square. PZ is 6 minus 2a, therefore PZ square is 6 minus 2a square plus ZQ square. ZQ is 3 minus a, therefore ZQ square is 3 minus a square. So in conclusion, we shall find out that a plus 3 square equals to 6 minus 2a square plus 3 minus a square according to the Pythagoras theorem. We'll open the brackets on both sides of the equation, and we find out actually here we have a plus 3 square is a square plus 3 square, that is 9, plus 2 times a times 3, that is 6a, and equals, on the other side of the equation, we have 6 minus 2a square. 6 minus 2a square is 6 square, that is 36, plus 2a square, that is 4a square, minus 2 times 6, that is minus 12, and minus 12 times 2a is minus 24a, plus 3 minus a square. 3 minus a square equals to 3 square, that is 9, plus a square, minus 2 times 3 times a, that is minus 6a. So here we have a square on both sides of the equation, so a square will get cancelled. We have also 9 on both sides of the equation, so 9 also will get cancelled. After we cancel those two expressions, in this side of the equation we left only with 6a. On the other side of the equation we have 36 plus 4a square minus 24a minus 6a is minus 30a. So in conclusion, we found out that 6a equals to 36 plus 4a square minus 30a. Here we subtract 6a from this equation and get that in this side of the equation we left with nothing, that is to say 0. In the other side of the equation we have 36 plus 4a square minus 38 minus 6a is minus 36a. Here we divide this equation by 4 and we get that 4a squared over 4 is a squared, minus 36a over 4 is minus 9a, and 26 over 4 is 9. 0 over 4 is 0. So in conclusion, we found out that a squared minus 9a plus 9 equals to 0. So here, this is the quadratic equation. And the general formula for quadratic equation is ax squared plus bx plus c equals to 0. This is the general formula. A, b, and c are the coefficients of this quadratic equation, and x is the variable that you are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Now a specific quadratic equation, that is to say a squared minus 9a plus 9 equals to 0. The variable that you're looking for is a, so x equals to a, the coefficient a equals to 1, the coefficient b equals to minus 9, and finally the coefficient c equals to 9. The only thing that is left to do in order to find out the value of a, that is the radius of this small circle, that is the radius that we are looking for in this question. The only thing that is left to do is to put the data of our specific quadratic equation inside this general formula for a, and this way we find out the value of the values of a, because x equals to a. We do it now, and we get that again x equals to a, so write down a equals to minus b. B is minus 9, therefore minus b is minus 9, that is plus 9, plus minus square root of b squared. B is minus 9, therefore b squared is minus 9 squared, that is 81. Minus 4 times a is 1, so minus 4 times 1 is minus 4, times c is 9, so minus 4 times 9 is minus 36. So inside the root we have 81 minus 36 divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So we found out that a equals to 9 plus minus. Inside the root we have 81 minus 36 is 45, so we left only 45 inside the root, divided by 2. So here we have two solutions to the possible for a. The first solution for a is that a equals to 9 plus 4 to 45 over 2. A is the radius of this small circle, that is the radius that we are looking for. According to the first solution for a equals to 9 plus 4 to 45 over 2. This expression 9 plus 4 to 45 over 2 is greater than 3. So according to the first solution, for a, the radius a of this small circle is greater than 3 units. But it is impossible that the radius a of this small circle is greater than 3 units because of the fact that the radius of this big semicircle equals to 3 units. And the big semicircle is definitely greater than the small circle, and therefore the radius of the big semicircle that equals to 3 must be greater than the radius of this small circle, and therefore the radius of this small circle a must be less than 3. But according to the first solution for a, the radius of the small circle A is greater than, is greater than 3. So this solution is the correct solution. We cancel the solution, and we left only with the second solution that is possible for A. The second solution for A is that A equals to 9 minus 4 to 45 over 2. So A equals to 9 minus 45 is 9 times 5, so we substitute 45 by 9 times 5 divided by 2. So according to the second solution, the radius A of the small circle that is the radius that you are looking for in this question, the radius A equals to 9 minus the square root of 9 is 3, so inside the root we left only with 5. So conclusion, according to the second solution for A, the radius A of the small circle equals to 9 minus 3 times square root of 5 over 2. Or in terms of numbers, the radius A of the small circle equals to 1.146 units in its length. Repeat again, we actually found out that the radius A of this small circle equals to either 9 minus 3 times square root of 5 over 2 units. In terms of numbers, the radius A of this small circle equals to 1.146 units. That is definitely less than 3 units. That is the radius of this big semicircle. In the next step, I will summarize the lecture. In this lecture, we found out the radius of this small circle. So in the drawing, we have the big triangle ABC, the big right triangle ABC. We know that side AB of the right triangle ABC equals to 6 units in its length, side BC equals to 8 units in its length. This is again ABC that is the right angle. In addition, inside this right big triangle ABC, we have this small circle and we have also this big semicircle. Our mission is to find out the radius of this small circle. So first of all, we implemented the Pythagoras theorem on this right big triangle, triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse on this big right triangle ABC is AC, so the square of the hypotenuse is AC square, and AC square must be equal to AB square plus BC square. Repeat again. According to the Pythagoras theorem, in the right triangle ABC, AC square equals to AB square plus BC square. AC is the missing side, so we leave it as it is. AC square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36. Plus BC square. BC is 8, therefore BC square is 8 squared, that is 64. So in total, we found out that AC square equals to 36 plus 64, that is 100. So AC square equals to 100. We took out all of this equation and finally found out that the missing hypotenuse AC equals to the square root of 100, it is 10. So therefore the hypotenuse AC is 10 units. In the next step, we defined the relevant points to this question with letters. We defined the center of this small circle, this point is point P. We defined the center of this big semicircle, this point is point Q. Likewise, we defined the point of tendency of tangent AB with this small circle, this point is point N. We define the point of tendency of tangent AC with this small circle, this point is point K. We define this point of tendency of tangent AC with this big semicircle, this point is point H. And finally, we define the touching point of the small circle with this big semicircle, this point is point L. Okay, now we can implement here rule 2. If we focus on this example point A, for this example point A, we have two tangents to this circle, tangent AB and tangent AH, and according to rule 2, they are equal to each other. That is to say, AB equals to AH. Okay, again, according to rule 2, AB equals to AH. but AB is 6 according to what is given in the question, so we can write here that AB is 6. And for this equation, 6 equals to AB equals to AH, we will derive that AH equals to 6. AH equals to 6. What is the roof of the missing line segment HC? HC equals to AC, that is 10, minus AH, that is 6. So in total, HC equals to 10 minus 6, that is 4. In the next step, we join points Q and H together by straight line. Point Q is the center of the big semicircle, point H is the point of the big semicircle itself, therefore QH is the radius of this big semicircle. We define the radius of this big semicircle as B. So QH equals to B. You can implement here all 1. Why? Because we have the radius QH, that is 1 to point H, that is the point of tendency of tangent AC with this big semicircle. And whenever you have a radius that is 1 to the point of tendency, then tangent AC will be perpendicular to the radius HQ. If AC is perpendicular to HQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So by doing this construction, we can do the right triangle, triangle HQC. In the right triangle HQC, we have, this is angle C. So angle C belongs to the right triangle HQC, but angle C belongs also to the big right triangle ABC. So angle C is a common angle that belongs to both triangles. So we define the size of angle C as alpha. So in the right triangle HQC, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, if you focus on the big right triangle ABC and the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. According to the same rule, that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we proved that the big right triangle ABC is similar to this whole right triangle, triangle HQC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles, so we can write down that angle alpha equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we can prove that all the triangles of the right big triangle ABC are correspondingly equal to all the triangles of the right small triangle HQC. Therefore those two right triangles are similar to each other according to angle similarity rule. Once again, we can found out that the right big triangle ABC is similar, this is the sign of similar to the right small triangle ACQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB of the right big triangle ABC over side HQ of the small right triangle HCQ equals to side BC of the big right triangle ABC over side HC of the small right triangle HCQ. Repeat again. We will derive the side AB of the big right triangle ABC over side HQ of the right small triangle HCQ equals to side BC of the big right triangle ABC over side HC of the right small triangle HCQ. AB is 6, HQ is B, it is the radius of the big semicircle, BC is 8, and HC is 4. So in conclusion, we can found out that 6 over B equals to 8 over 4. 8 over 4 is 2, so we can found out that 6 over B equals to 2. We multiplied this equation by B, and finally found out that 6 equals to 2B. We divided this equation by 2, and finally found out that the missing radius B equals to 6 over 2, that is 3. So here HQ, that is the radius of this big semicircle, that equals to B is equals to 3. QB is also the radius of this big semicircle, that is equal to 3. In the next step, we join points P and N together by straight line. Pn is the radius of this small circle. We define the radius of this small circle as A. A is the radius that we are working for in this question. Okay, we can implement here all 1 because we have the radius Pn that is equal to A. The radius Pn is 1 to point N, that is the point of tendency of tangent AB with this small circle. And whenever you reduce that is 1 to the point of tendency, then tangent AB will be perpendicular to the reduced NP. If AB is perpendicular to NP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points P and K together by a straight line. PK is the radius of this small circle, that is equals to A according to our definition. The radius PK is 1 to point K, that is the point of tendency of tangent AC with this small circle. And whenever radius is 1 to the point of tendency, then tangent AC will be perpendicular to the radius KP. If AC is perpendicular to KP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, I presented to you a new rule and implemented a new rule in our drawing. The new rule is rule 15. According to rule 15, from an external point of a circle, you draw two tangents to that circle, then the angle that will be created between the two tangents is angle bisector must pass for the center of the circle. So in the drawing, this is the common external point P. From this common external point P, we draw two tangents to this circle, tangent PA and tangent PB. By drawing the two tangents PA and PB, we created this angle APB. Angle APB was created by drawing tangent PA and tangent PB to this circle. So the angle bisector of this angle APB must pass point O, that is the center of this circle. Again, the angle bisector of angle APB that was created by drawing tangent PA and tangent PB. The angle bisector of this angle APB must pass through point O, that is the center of this circle. We can actually implement rule 15 in our drawing. Why? Because in our drawing, if we focus on this common external point A, from this common external point A, we have two tangents to this small circle, tangent AN and tangent AK. By drawing the two tangents AN and AK, we created the angle A. Angle A created by drawing tangent AN and tangent AK to this small circle. And according to rule 15, the angle bisector of this angle A must pass for point P, that is the center of this small circle. Again, the angle bisector of this angle A that was created by drawing tangent AN and tangent AK, the angle bisector of this angle A must pass for point P, that is the center of this small circle. So we can actually know that the angle bisector of angle A passes for point P, that is the center of the small circle. So PA is the angle bisector of angle A. If the size of angle A is 2 theta, then the angle bisector of PA bisects angle A into 2 halves. Each half equals to theta. Likewise, if we continue to focus on this common external point A, from this common external point A, we have two tangents to the big semicircle, tangent AB and tangent AH. Actually, by drawing the two tangents AB and AH to this big semicircle, we get the same angle A. Now we can implement rule 15. According to rule 15, the angle bisector of this angle A must pass through point Q, that is the center of this big semicircle. Again, the angle bisector of this angle A must pass through point Q, that is the center of this big semicircle. So you can see here that the angle bisector QA bisect angle A into 2 halves. Each half equals to theta. So in conclusion, you can write down that the angle bisector of the same angle A passes also for point Q. And it is obvious that the angle bisector of angle A must pass also from point A. So you can write down also that the angle bisector of angle A passes also from point A. In conclusion, actually found out that the angle bisector of this angle A passes through points A, P and Q. Repeat again. Actually found out that the angle bisector of angle A passes through points A, P and Q. And we know that the angle bisector of angle is a straight line. The angle bisector of angle is a straight line, and especially the angle bisector of this angle A, is also a straight line. Okay. the angle bisector of angle A is a straight line. So therefore all the 3 points A, P, and K are located on the same straight line. And the straight line is the angle bisector of angle A. Okay, so all the 3 points A, P, and Q are located on the same straight line, because all the 3 points passes for the angle bisector of angle A. The angle bisector of angle A is a straight line, so all the 3 points are located on the same straight line, that is the angle bisector of angle A. Okay, all the 3 points A, P, and Q are located on the same straight line, that is the angle bisector of this angle A. Or we can also write down that line segment APQ is one straight line. Again, line segment APQ is one straight line. Line segment APQ is one straight line. And because of the fact that line segment APQ is one straight line, it means that this angle theta is a common angle that belongs to the small right triangle A and P, and angle theta also belongs to the big right triangle ABQ. So in the right big triangle ABQ, this angle equals to theta, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, this equals to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the right triangle ANP, the right small triangle ANP, this angle equals to theta, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus theta according to the sum rule, that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we proved that the big right triangle ABQ is similar to this small right triangle ANP. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both triangles, so we can write down that angle theta equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So I should prove that all the figures of the right big triangle ABQ are corresponding equal to all the figures of the right small triangle ANP. Therefore, those two right triangles are similar to each other according to angle similarity rule. So if it again, I should found out that the right big triangle ABQ is similar to the right small triangle ANP according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB of the right big triangle ABQ over side AN of the small right triangle ANP equals to side BQ of the big right triangle ABQ over side NP of the small right triangle NP. Repeat again, we will derive that side AB of the big right triangle ABQ over side AN of the small right triangle NP equals to side BQ of the big right triangle ABQ over side NP of the small right triangle ANP. AB is 6, AN is the small in the missing side, so we leave it as it is. BQ is 3, it is the radius of the big semicircle, that is equals to 3. BQ is 3, NP equals to A, it is the radius that we are looking for in this question, it is the radius of the small circle, so NP is A. So in conclusion, we actually found out that 6 over AN equals to 3 over A. Here we cross multiply this equation and finally found out that 6A equals to 3 times AN. Here we divided this equation by 3 and finally found out that the missing side AN equals to 6A over 3. 6A over 3 is 2A. So we actually found out that this missing side AN equals to 2A units in its length. So AN equals to 2A. AB equals to 6, and therefore the missing line segment NB must be equal to AB minus AN. AB is 6, AN is 2A, so in total the missing side NB equals to 6 times 2A. NB equals to 6 times 2A. From point P we do perpendicular on BQ. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point P and BQ. This point is point Z. By doing this construction, we can deduct quadrilateral NPBZ. In quadrilateral NPBZ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the quadrilateral NPBZ we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at its right angle flat a square. So we relate to quadrilateral NPBZ as a right angle because it has 4 right angles. But we also know that the opposite sides of right angle are equal to each other. So right angle NPBZ, side NP must be equal to the opposite side BZ, but NPZ, therefore BZ must be also equal to A. Likewise, according to the same rule, the same right angle NPBZ, side NB must be equal to the opposite side BZ. But NB is 6 ones to A, therefore PZ must be also equal to 6 ones to A. What is the length of the missing 97 ZQ? ZQ equals to BQ minus BZ. So ZQ equals to BQ, that is 3, minus BZ, that is A. So in total, ZQ equals to 3 minus A. We have an external notch between this small circle and this big semicircle. And that is to say they are touching each other externally at point time. Whenever you have an external notch between two circles, you can implement rule 10. I repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together must pass through their touching point. In the drawing we have two circles, the center of this, and they have the external between them at point P. That is to say they touch each other externally in this point P. The center of this small circle is at point M. The center of this big circle is at point O. The straight line that connects their centers together is the straight line MO. And according to this rule, Rule 10, the straight line MO must pass through point P, that is their touching point. Again, the straight line MO must pass through point P, that is their touching point, or MPO is right side line. Again, MPO is right side line according to this rule, Rule 10. You can actually implement Rule 10 in our domain, because in our domain, you have an external notch between this small circle and this big semicircle, that is to say they are touching each other externally at point L. And therefore, going to Rule 10, the straight line that connects the centers together, here, the center of this small circle is at point P, the center of this big semicircle is at point Q, and the straight line that connects the centers together is of course the straight line PQ. This straight line PQ must pass through point M, that is their touching point. Again, the straight line PQ must pass through point M, that is their touching point. Or P and Q is one straight line. Again, P and Q is one straight line according to Rule 10. If P and Q is one straight line, it means that PQ is also a straight line, but what is the length of PQ? PQ equals to PL plus LQ. Again, PQ equals to PL plus LQ. PL is the radius of this small circle, that is the radius that we are looking for, that is equal to A according to our definition, and LQ equals to 3, that is the radius of the big semicircle, that is 3. So in total we can find out that PQ equals to A plus 3. The next step, I copied the right triangle PZQ in a new page, and we implemented the Pythagoras theorem, this right triangle PZQ. Actually, this is the right triangle PZQ that according to the original domain. The hypotenuse PQ is A plus 3, PZ is 6 minus 2A, and ZQ is 3 minus A. According to the Pythagoras theorem, this right triangle PZQ, PQ square equals to PZ square plus ZQ square. Again, PQ square equals to PZ square plus ZQ square. PQ is 8 plus 3, therefore PQ square is 8 plus 3 square, and it must be equal to PZ square. PZ is 6 minus 2A, therefore PZ square is 6 minus 2A square, plus ZQ square. ZQ is 3 minus A, therefore ZQ square is 3 minus A square. So in conclusion, we can find out that A plus 3 square equals to 6 minus 2A square plus 3 minus A square. We open the brackets on both sides of the equation. A plus 3 square equals to A square plus 3 squared, that is 9, plus 2 times 3 times 8, that is 6A. On the other side of the equation we have 6 minus 2A squared. 6 minus 2A squared equals to 6 squared, that is 36, plus 2A squared, that is 2A squared, that is 4A squared, minus 2 times 6, that is minus 12, minus 2A. Minus 12 minus 2A is minus 24A, plus 3 minus A squared. 3 minus A squared equals to 3 squared, that is 9, plus A squared, minus 2 times 3 times 8, that is minus 6A. So here we have A squared on both sides of the equation, so A squared will get cancelled. We have also 9 on both sides of the equation, so 9 also will get cancelled. After we cancel those two expressions, in this side of the equation we are left only with 6A. In the other side of the equation we have 36 plus 4A squared, minus 24A minus 6A is minus 30A. So in conclusion, we can find out that 6A equals to 36 plus 4A squared minus 36A. Here we subtracted 6A from this equation, And finally found out in this side of the equation we have nothing, that is to say 0. In the other side of the equation we have 36 plus 4a squared, and minus 38 minus 6a is minus 36a. So in conclusion we can find out that 0 equals to 36 plus 4a squared minus 36a. Here we divided this equation by 4, and finally found out that 4a squared over 4 is a squared, minus 36a over 4 is minus 9a, and 36 over 4 is 9. In conclusion, we found out that a squared minus 9a plus 9 equals to 0, so this is a quadratic equation. And the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. We find out the value of x according to the following formula: x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, that is to say a squared minus 9a plus 9 equals to 0, the variable that we are looking for is a. So x equals to a, the coefficient a equals to 1, the coefficient b equals to minus 9, and the coefficient c equals to 9. The only thing that is left to do is to put the data of our specific quadratic equation in this general formula for a, and in this way we find out the values of a, because x equals to a. We did it and found out again that x equals to a, so a equals to minus b. b is minus 9, therefore minus b is minus 9, that is plus 9, plus minus square root of b squared. b is minus 9, therefore b squared is minus 9 squared, that is 81. Minus 4 times a is 1, so minus 4 times 1 is minus 4 times c is 9, so minus 4 times 9 is minus 36. So inside the root we have 81 minus 36 over 2a. a is 1, so 2a is 2 times 1, that is 2. So in conclusion, we found out that a equals to 9 plus minus. Inside the root we have 81 minus 36. 81 minus 36 is 45 divided by 2. So inside the root we left only 45. So here we have two solutions that are possible for a. The first solution for a is that a equals to 9 plus square root of 5 over 2. This expression 9 plus square root of 45 over 2 is greater than 3. So according to the first solution, the radius of this small circle is greater than 3 units. But it is impossible that the radius of this small circle is greater than 3 units because of the fact that the radius of the big semicircle equals to 3. And the big semicircle is definitely bigger than the small circle. Therefore, the radius of the big semicircle, that is 3, must be greater than the radius of this small circle. Or in other words, the radius of this small circle must be less than 3 units. But here, we found out that the radius of the small circle is greater than 3 units. Therefore, this solution is the correct solution. We cancel the solution, and we left only with the second solution that is possible for a, that is the radius of the small circle. According to the second solution, a equals to 9 minus 4 to 5 over minus square root of 45 over 2. 45 is 9 times 5, so substitute 45 by 9 times 5, and we found out actually that a equals to 9 minus square root of 9 times 5 over 2. The square root of 9 is 3, so inside the root we left only with 5. In conclusion, we found out that the radius of this small circle equals to either 9 minus 3 times square root of 5 over 2 units. In terms of numbers, it is equals to 1.146 units. This is less than 3 units. That is the radius of this big semicircle. Okay, thank you very much.